As I mentioned, the second family of statistics, the scan statistics, really evolved from the quadrat counts and take a similar approach in that they overlay a grid onto the points, or a regular grid, or a series of grids of different sizes, or a series of circles drawn on points in a grid of different sizes. There are many different variants, but they all boil down to the same idea. You draw a geometric shape and you count the number of events in that shape. And then you need a mechanism to figure out whether the observed number of events in your shape, typically a circle, is conformant with your null hypothesis of complete spatial randomness. And so to do that, you need some kind of reference value. And if the number of points is higher than the reference value, you say this is a cluster. If it is much lower than the reference value, you say there's inhibition going on. So that's the main idea behind these statistics. So in contrast to the quadrat count, which is a global statistic, these scan statistics are local statistics in that they actually pinpoint the location of the cluster. So the principle, very simple. We put a grid over the points on each of the crossing points, the vertices in the grid. We draw a circle. We count the number of events in that circle. We move it over. We draw the circle again, count it again. And we need a reference. And how do we get the reference? In the early methods, in the GAM statistic, that was done by replicating the point pattern many times and recounting for all of these random patterns. And then when you get a number that is much higher than the empirical distribution from your random points, then you say it is significant. Now there's two different ways to get our random points. So basically, the null hypothesis is that under spatial randomness, the risk, the intensity, if you wish, is the same. It's uniform everywhere. And these kinds of tests are usually applied in context where you're interested in the difference between the patterning of cases of events and the patterning of controls. For example, the cases would be addresses of people with a disease. The controls would be the addresses of the population at risk. So you have two sets of points. One are the cases, the others are the controls. Then how do you express constant risk? The constant risk is when the ratio of cases to controls is constant throughout. So one way to implement this is to simulate a constant risk. So you have a total number of points, and the number of those that are cases is the same no matter where you are. So let's say if you have 100 points, 5 of these are cases. So 5 out of 100 points are cases, which means you have 95 controls and 5 cases. So your ratio is n1 cases, 5, over n1 plus n0, 5 plus 95, 100 total points. So if we keep this proportion constant in the simulation, then we mimic a uniform risk pattern. Now there's a catch here, and we saw this a little bit in the last lecture as well. When we simulate this with a constant risk, we don't necessarily get the same number of points each time. So in this kind of simulation, and this is referred to, as I mentioned, as a constant risk simulation, the number of cases that we actually get, the n1, varies slightly from simulation to simulation. The proportion is the same. It's like throwing dice. You know, if you throw dice, you get 1/6, if it's a proper setup, you get 1/6 of a chance to get a particular number. So if you throw in enough times, you will get 1/6 of the cases to be, let's say, 1s. But that doesn't mean that if you throw 6 times, that you get 1. If you throw 6,000 times, the proportion will start to approach 1/6. But if you do a smaller number, sometimes it will be 1, sometimes it will be 2, sometimes it will be none. That's the same thing here, even though the proportion is fixed. The actual risk is uniform. So that's one way of simulating randomness. The other way of simulating randomness respects the total number of cases. So it looks at the points, the same 100 points, and say, randomly we're going to pick 5 of these and call them cases. And so now we're going to do it again and pick 5 other ones, maybe. Some might be the same, some might be different, and these will be the cases. But each time we do this, we have exactly 5 cases. So the number of cases, the N1, is fixed and under control. This kind of simulation is called random relabeling, because essentially what we're doing is we're taking the 100 points that we have and we're changing the label of the point. Is this a case or is it a control? We change that randomly given the proportions that we have of the number of cases over the number of controls. So this is like a permutation approach. Instead of shuffling the points around, we don't shuffle the points around, we shuffle the labels around. So there are 5 labels on those 100 points that say disease, and we're just randomly sticking them on other points. The points themselves don't move, the number of points doesn't change, but the labeling does change. This is another way of mimicking randomness, because basically what we're saying is that the chance that one of these labels lands on any given point is the same for all the points, which is our uniform risk assumption, which is what we need in complete spatial randomness. So those are the 2 ways in which we can play with our points to mimic randomness. And remember why we do this, because we need a reference. We need a reference count for the number of events in our circle. So we have our actual point pattern, and we do these circles and count how many points we have. And then we generate a lot, 1,000, 10,000 fake point patterns that follow this uniform risk null hypothesis. And for each of these, we also count the events in our circles. And if we find that one of our circles has many more points in it, many more events in it, then our reference distribution tells us it should have, then we say we reject the null with a given p-value. And there are several examples in the literature of these kinds of statistics. As I mentioned, an early one is the geographical analysis machine, which is basically a brute force counting of events in circles. Stack is kind of a variant of that. There's several problems here, and these problems have been fixed to some extent in the Koldorf's scan statistics, because he introduced a much more formal statistical framework to analyze this. But one of the problems is obviously overlapping circles. So you have multiple comparisons, as it's called in the statistical literature. You're using the same data over and over and over in multiple tests. So some of the information that is in one of these circles is already in one of your other circles. I mean, previously we called this spatial autocorrelation. This is spatial autocorrelation to the extreme, so that needs to be taken into account. And in the naive early implementations, this was not. It's also sensitive to the size of the circle. You take a small circle or a large circle, this will affect the number of points you count in the circle. And so there's a certain arbitrariness here, and the scan statistic that you will be working with, in fact, uses increasing diameters or radii of the circles and recomputes it each time. And then, as I already mentioned, the multiple comparisons is a real problem in terms of figuring out what is the true p-value. Multiple comparison is the following problem. If you do 2 tests with the same data, then the p-value, that's the probability of rejecting the null when the null is in fact true, your type 1 error. your p-value of the combined tests is not the p-value that you use for each of the tests individually. So you say you do test 1 and you take p-value 0.05, and you do test 2 and you do p-value 0.05 again. The p-value for the combined experiment of these two test statistics is not 0.5. It's much higher. So to take that into account properly, it's actually very difficult to do, but there are a number of techniques. One of these is called the Bonferroni bound technique. And that essentially consists of dividing your target p-value by the number of tests that you carry out. So let's say our target p-value was 0.05. We do 2 tests. So in each of these tests, we should use 0.025 as the p-value and not 0.05. And you can easily see, if you do 10 tests, it would be 0.005. If you do 1,000, and so on. And in the scan statistics, you typically draw thousands of these circles. So as a result, the p-value is very difficult to establish because of these multiple comparisons. And that was one of the drawbacks. What does that mean in practice? If you ignore this, you get a lot of false positives. You get a lot of things that you identify as clusters which in fact are not, because the p-values that you use are wrong. They don't properly reflect the uncertainty in the data, which is what it's all about. And this was a major criticism of the GAN, the geographical analysis machine, that it yielded so many false positives. This was developed by Openshaw and his team. And it was very controversial because it was used in a couple of very well-documented cases of tests for leukemia clusters in the UK. And what tended to happen is that the GAN would find clusters whereas other techniques would not. And so then it was this whole discussion, are these real clusters or are these fake clusters? And if you read Openshaw carefully, he never actually makes a strong claim about the significance of these clusters, but sees it as an exploratory device. It's a way to go, it's actually more like machine learning. In computer science, data mining is a form of machine learning where the machine doesn't learn, but you write a program so that the information in the data gets extracted in an automatic fashion. So you don't have to sit there and draw all these circles. The computer does it for you and then comes up with a map and says, well, here are the clusters. So that's an exploratory device. Same problem in data mining. You also have problems of false positives and this multiple comparison issue that pops up there as well. So this is an example of a result using the Cardiff juvenile homicides again. We get these kinds of ellipses in stack which then say, well, this is a cluster, and so on. So rather than drawing a conclusion for the pattern as a whole, we draw location-specific conclusions within these ellipses. Now, the one that we'll spend a little bit of attention to is the scan statistic as developed in a number of papers by Martin Koldorf. And again, it's in the case control setting, and what he did was introduce a more, if you wish, a more formal probabilistic framework into this analysis by actually using a likelihood principle, which I'll talk about in a minute. So it's not really pure pattern in terms of what we did before, where we were just looking at the points as events, period. This only really works when you have two kinds of points, one being the cases, the other being the controls. And there's two statistical settings here that each will lead to a different distribution and a different test. The one is called the binomial setup. And this is the setup where you actually have event points. So you have addresses of people with the disease and addresses of the population at risk, of the reference population. And because of that, we will have a probability that a case is counted in the circle versus the probability that it's not counted in the circle. And this is basically a binomial distribution. Whereas the second setup is when you have aggregation of counts by areal unit. Say you have counties or census tracts and the number of people with leukemia in the census tract. So you don't have the individual addresses, but you have an aggregation of these events. So then the distribution that we use is a Poisson distribution for counts of events within a particular areal unit. We've already used this. This is the distribution that underlies complete spatial randomness, but here we'll use it in a specific context of how many points can we expect to have in a given areal unit. Of course, given a parameter of the average intensity of the process, which we need. So these two cases, one works when you have actual locations of the events. The second one works when they are aggregated, which is actually much more common in practice. In practice, very often, the individual locations are not disclosed because of privacy considerations. So, and even if they are disclosed, sometimes they're randomly altered, so they're not really in the position where they show up on the map. So then it's really not, if you're going to draw circles and count points in the circles, and these points have been moved, then some points that should be in the circle are not, and some points that should not be in the circle might be in the circle. So this affects the results of the analysis. The statistical framework behind this uses a concept of a likelihood, and I'm not assuming that everybody's familiar with this, and I will spend a little more time on this later on when we deal with the regression analysis. But basically, you know, in my words, likelihood is the probability that you observe the data given a particular probabilistic model. So, say given that the distribution of heights of people is a Gaussian, a normal distribution with a mean of whatever, you know, 5'7" and a standard deviation of a foot, okay? What is the probability that the lengths of the people in this class fits that distribution? That is a likelihood. So of course, the higher the probability that this is the case, the closer we will be to the true, to correct distribution of this characteristic. And that's the idea. In practice, we flip it around and we try to find the parameters of the distribution that for which the data that we see have the highest possible probability. So they're the most likely to come from that particular distribution. And that's the likelihood principle. So what Kovdor did is introduce this likelihood principle in the construction of the scan statistics. So he draws as the same thing, as a bunch of circles, and either counts the points or the counts within the circle, and then finds those circles where the likelihood, the probability that the count of events comes from a particular distribution is the highest possible. It maximizes the likelihood. So then that's one thing. That is your candidate to be a cluster. Then whether or not this is a cluster is done with a randomization technique. So you randomly replicate the points, you redo this exercise, you identify the circle with the highest likelihood, and you put that in your reference distribution. You do this 1,000 or 9,000 times. This gives you a reference distribution of these likelihoods, and then you see where the one that you have for your point pattern rates in terms of the reference distribution. That's, in words, basically the idea behind this. And now for the two cases, we have a different statistic. For points, we use the binomial, and then we find a circle. So this is not just all the circles with the same radius, but circles with changing radius. We find the one where the statistics, this t, is maximized. And this is basically looking at the proportion of the cases inside over the total number of points inside to the power, this is where the binomial comes from, of the number of points, the number of cases inside. And the same thing for the ones outside. So you're basically comparing a ratio of how many cases do I get within my circle as a proportion of the points in the circle versus outside of the circle. And you maximize, you find, let me put it differently, you find a circle for which this number is the highest possible number. And that is your candidate cluster. In the second case, second case is the next slide. The p-value is based on randomization. So you do this many, many times, and this gives you a t statistic, capital T, not your student T, a scan statistic for each of the random sets. Let's say we use random relabeling. So we have 1,000 points and we have 50 diseases in that points. So we keep our 1,000 points, but we randomly allocate the 50 diseases to different locations. We recompute all our circles. We find a circle with the highest ratio of these, cases in versus cases out type of ratio. And we record that number. Let's call that TR. Then we do it again. Relabel, do all our circles. You can see this is very computationally intensive. There's a lot of number crunching. And again, identify the maximum and do this over and over again. This gives us a reference distribution, and then we see where the one is that we actually observe. If that is the highest one, let's say we do 1,000 of these, then the p-value, pseudo p-value, is 1 over 1,000. Actually, we do 999 of these. The p-value is 1 over 1,000. So that is a pseudo-significance. That's not a true p-value because it's based on this random relabeling randomization procedure. As I mentioned, if we have counts of events by area, we use the Poisson distribution, which gives us a slightly different but very similar kind of test. You see this is inside, observed over expected, outside, observed over expected, raised to the number of observed inside and the number of observed outside. And you'd only do it for those cases where the ratio in the circle is higher than the ratio outside the circle. It's actually a one-sided test. If you're interested in clusters of low events, you just flip this around. So you look at the circle, you compute these ratios. If there is, in a sense, a higher density of cases inside your circle than outside your circle, you keep it. And you compute the statistic. If it isn't, move on to the next circle. Okay? And then, same thing again, you simulate under the no, random, constant risk. You get your p-value, pseudo p-value, from the proportion relative to the reference distribution. And then you get a nice map. Let's say this is prostate cancers in Appalachia. This is real data, age-adjusted rates, and you run Satscan on this, and you find these two quote-unquote clusters of elevated prostate cancer. Now, if you look back at the map, it's kind of a stretch. How does this come to be a cluster? It's because you're manipulating two things, the location of the circle, but also the radius of the circle. So these statistics, these maxima, are computed for all these different types of circle, and if it turns out that the highest of the high is a large circle, then you get something like this, which you have to think of as a point centered in the middle of one of these counties with a circle around them that includes all these other counties that are dark red. And same here. So this is the core of the cluster with a circle around it that identifies the counties as being part of that cluster. And you can have, in Satscan, you can have different levels of clusters. You have to be very careful when you apply Satscan because there's a p-value for each. And it's not because Satscan identifies it as a cluster that it's necessarily significant. This is a point of confusion for newbies, as they say, if you use this the first time. Satscan spits out a lot of stuff, but not necessarily all of these locations are significant clusters. And as I said, it's a one-sided test, so you can flip it around. If you're interested in low clusters of low prostate cancer, then you only take the circles where the density, if you wish, inside the circle is less than the density outside the circle. So it's the other way around. You only compute the statistic if the proportion of observed over expected inside the circle is smaller than the proportion outside the circle. And then you do the whole procedure again. You get these t-values, you get the highest likelihood, you get a reference distribution, and that gives you pseudo p. Here we have 4 of these clusters of low prostate cancer. And again, you have to think about this back in terms of a circle centered on some county that is counting all the events within that circle. So it's not necessarily intuitive, but this is by far the most commonly used statistic. So in public health, Satscan is used by just about every agency to identify clusters of just about anything you can think of. And as I said, it works in 2 different cases, and so it's up to you to identify which case you have. You either have individual events with locations, or you have aggregates of counts by area, which the first case gives you a binomial distribution, the second case would give you a Poisson distribution. Okay?